Okay, fine. So this is your 4 momentum. Okay. Now if you take P mu, if you consider P mu, okay, P upper mu, P lower mu, okay, then you will see that this will be equal to m square. By definition, it will be m square for velocity u mu, okay, but for velocity is c square, so it is m square c square. Okay, clear? But P mu, on the other hand, P mu is equal to P0 P lower 0, okay, minus vector P square, okay, but P upper 0 is same as P lower 0, so it will be P0 square minus vector P square, okay. So this is, so if you use this relation here, okay, you will get E square, E equal to plus or minus square root of P square C square, okay, that is P square C square plus M square C to the power 4. So this P is P dot P. Hmm? So there are two signs of energy. Because you will, if you substitute it here, you will get E square equal to P square C square plus M square C to the power 4. So E is plus or minus square root. Okay, so these are the simple thing which I forgot in the previous class. Okay, fine. Okay. Now we are discussing about the dynamics of relativistic free particle. Okay, and I introduced the action for a relativistic free particle. Okay, by imposing the invariance under Lorentz transformation. Okay, and the dimensionality. Okay, we argued that the action must be equal to, action must be equal to minus mc square d tau. Okay, clear? So now let me write, so this I will just erase, this is not useful here. Okay, I'll just erase, or maybe I will keep it and then I will go to the next page. Okay, so my action is minus mc square d tau, okay, between tau 1 and tau 2. Okay, fine. So as it's, this is completely relativistically invariant, that means Lorentz invariant action. Okay, suppose now this tau is a proper time in the coordinate time, that is in the coordinate time, in the coordinate time t. Suppose I want to write this action in the coordinate time. Okay, so obviously expression like this, suppose if L is the Lorentz scalar, okay, some Lorentz scalar is there, okay, that means this quantity is a scalar under Lorentz transformation. Okay, then obviously this doesn't work, right, because dt will transform under Lorentz transformation. Okay, clear? Hence this action will not, overall this action will not be Lorentz invariant because of this factor. Is that clear? Okay, I want to write this action in the coordinate time, but it should be relativistically invariant or Lorentz invariant. Okay, so that one can do easily. Okay, so s equal to minus mc square. Instead of d tau, I will write it as dt and d tau by dt, chain rule. Okay. And then, yeah, so dt and d tau by dt. Yeah, so d tau I have written like dt, d tau by dt. Okay, but what is d tau by dt? Minus mc square dt. Okay, d tau by dt is just square root of 1 minus v square divided by c square. Okay, where v is your usual velocity. Okay, okay, so it looks like it is Lorentz, it does not transform as a scalar under Lorentz transformation because I have written in terms of v and t, but this whole combination is actually Lorentz invariant because this is nothing but data which is Lorentz invariant quantity. Okay, so this S is actually Lorentz invariant. This S is Lorentz invariant. Hmm? Okay, so either you write this action in this coordinate time, okay, then it becomes like this, or you keep at this level. Okay, I will postpone or I will give this as an exercise. I will come back to this. Okay, we have to, if I want to write the action in covariant form, if I want to keep the action in manifestly covariant form, that means like this. Okay, then I have to do something else. I have to I have to be very careful here. Okay, but I have chosen for some reason to write this action in coordinate time. I will write that so that the final expression is still Lorentz invariant. You see, difference between this part and this part is that this is manifestly Lorentz invariant. By just saying that, by knowing that proper time is Lorentz invariant, you conclude that S is Lorentz invariant. Okay, so it is manifestly Lorentz invariant. On the other hand, this is not manifestly Lorentz invariant. Manifestly means just by looking at it, you cannot tell whether it is Lorentz invariant or not. But it is actually Lorentz invariant, okay, through this. Clear? So this is your action. Okay. So what is your Lagrangian? The Lagrangian, you identify now Lagrangian. So S is, you compare with your usual definition. Okay. So L will be equal to minus mc square, okay, square root 1 minus v square divided by c square. Is it clear? Okay, where v is this. Okay. Now given the action, given the Lagrangian, you can calculate Euler-Lagrange equation of motion. Lagrange equation of motion. What are the Euler-Lagrange equation of motion? Okay. Recall from the classical mechanics that Euler-Lagrange equation of motion is given by d by dt of del L by del x. There are three coordinates, xi dot minus del L by del xi equal to 0. I runs from 1, 2, 3. And since I have written now in the coordinate form, okay, there is no, the metric is not coming now. Now on this vector, whether I write axi or xi doesn't matter because we are in 3 space now. Okay, is that clear? I have written it in once I written it in a coordinate form. Okay, x mu or p mu or v mu will not come. Okay, I will be having xi's, okay, 3 indices, just mu will not come, there will be i's. Okay, and now whether you write I up or I down, it doesn't matter. Okay, yeah. On the other hand, if I use this form, if I use this form, okay, it really matters. Okay, it's in the these are Lorentz indices. Okay, mu runs from 0, 1, 2, 3. Okay, whereas here I'm just concentrating on 3 components. Okay, there is I given by index I. Okay, so let us calculate this equation of motion. Okay, so if you note that the V is dx by dt or Vi is dx by dt. Okay, okay, then you can calculate the equation of motion. Okay, so the equation of motion, okay, from this, so you can see that this Lagrangian does not depend on xi. Okay, so you can write this Lagrangian as minus mc square minus mc square, okay, 1 minus x dot vector x dot vector x dot divided by c square half. Okay, okay. Okay. Yeah. So now I will compute this. You can see that this Lagrangian is independent of xi's. Okay, the velocities are coming, but the coordinates are not coming. So this term will not contribute. Second term. Okay. Del L by del xi dot is equal to minus mc square, okay, 1 over twice square root 1 minus x dot. I will write, I'm differentiating this quantity, so I will write this as v square divided by c square again, and differentiation of this with respect to xi dot. Okay, so d dt d sorry, there will be partials. Del xi dot, okay, and this is a dot product, so I will use x dot j, and as I told you, I don't have to bother about upper and lower now, because I have written it in with respect to three vectors. Okay, so what is this differentiation? Okay. Differentiation will be minus mc square, okay, and then there will be one Kronecker delta when I differentiate this, and this will come, plus this will remain, and differentiation of this, there will be another Kronecker delta, so they will add up and I will get twice, so these two will go. Okay, so I will get minus mc square, okay, and the Kronecker delta will give me xi dot divided by square root of 1 minus v square divided by c square. Okay, clear? Fine. So this is your del by del xi dot. This is my del L by del xi dot. Okay. Now the Euler-Lagrange equation becomes, now I have to differentiate this with respect to time. Okay, I have to differentiate this quantity with respect to time. Okay, note that this quantity 1 over square root of 1 minus v square upon c square is gamma. Okay, so I will write this as minus mc square gamma, okay, xi dot. Okay.
Sir, there will be a factor of minus 1 by c square also, right? When we differentiate.
Yeah, minus 1 by c square, so it will be minus c square here. Okay, so this will go, so this factor will go, correct. Okay, so it will be, so this is m gamma xi dot. Now d dt of del L by del xi dot is equal to 0 implies, okay, d dt of m gamma xi dot equal to 0. But what is m gamma xi dot? It is just a pi. Okay, so this is equal to d dt 3 momentum, d dt of pi equal to 0. So this is what we expect for a free particle. Okay, so where pi is m gamma xi dot. Okay, so you have, since dpi by dt equal to 0, you have 3 momentum conservation of 3 momentum. Okay, clear? Fine. So these are my equation of motion, Euler-Lagrange equation of motion. Then nothing but it tells you that momentum is constant of motion. Momentum is constant. Okay. Is that clear? So you can also write this as m times d2 xi by dt square. Okay. M times d2 xi by dt square. That is also, you can m gamma d2 xi by dt square. No, you cannot write because there is a t, so gamma is there. Yeah, but gamma Yeah, but it is good practice to keep it at this level. You don't have to write in terms of xi. Okay. Fine. Also, what is your canonical momentum? Given the Lagrangian, the canonical momenta pi is given by del L by del xi dot. Recall from classical mechanics, canonical momenta in the Lagrangian framework, the canonical momenta are given by this relation. Okay. Now it is an easy exercise to check that del L by del xi dot is actually this. Okay, this is what we have done. Okay, del L by del xi dot is this. Okay, so pi matches with our three momentum definition. The canonical momenta, in this case, the canonical momenta, this is your canonical momenta. Okay, canonical momenta are always calculated through this relation. Okay, this matches with our earlier definition of pi, three momentum. Why I'm stressing this fact? Because when you consider electromagnetic field, it is not necessary that uh, canonical momenta is equal to mechanical momenta. There will be some change. Okay. Hmm? But for free particle, relativistic free particle, the canonical momenta calculated from the given Lagrangian of free particle matches with your usual definition of three momenta. Okay. Now I have equation of motion, Euler-Lagrange equation of motion. Then I have the canonical momenta. What you do next? Okay. Next is to calculate the Hamiltonian. What is Hamiltonian? Hamiltonian from the Lagrangian. If I want to calculate the Hamiltonian, how you calculate? It is the definition is P dot V minus L. PQ dot minus L. Okay. So now you use this P. Okay. You use V. Okay. And you know L. Okay. You have to calculate this. Okay. But to make the calculation simpler, okay, you note the fact that uh, you note the fact that our P is given by m gamma V. This is m times V divided by square root of 1 minus V dot V divided by C square. Okay. Now Hamiltonian is a function of P and X. Lagrangian is a function of X and X dot. This you should know. Okay, there's a basic difference between Lagrangian and Hamiltonian. Hamiltonian, you should not, you should never write Hamiltonian as X in terms of X and X dot. That is wrong. Okay, Hamiltonian is always written in terms of momentum and coordinate. Lagrangian is always written in terms of X and X dot. Even if you know x dot as a function of p, you should not put it p here. That is the wrong way of substituting the velocity it has no meaning. Okay, Lagrangian is always defined in terms of coordinate and velocities. So x dot are configuration space variable and xp are phase space variable. So in the classical, from the classical mechanics, you should know at least this. So here what you need to do, you have to invert this. You know, we know the relation between p and v. Okay, it is this. Okay, you have to write, you have to express v's in terms of p. Okay, so you have to substitute for v a function of momenta p. Okay, and in the Lagrangian also there was this factor v, right? This also you should write in terms of momenta. And substitute here, and then you calculate the Hamiltonian. It is useful to note that through this relation, okay, you can play around this relation and show that the gamma, which is basically this factor, okay, 1 over square root of 1 minus v square upon c square, gamma can be written, or first I will write the velocity. Okay. So v can be written in terms of p as c square v square. So that is what is required actually, v square, to write the gamma. Okay, c square p square divided by p square plus m square c square. You can write this. Okay, just use this relation. Take dot product with p again. You will get v square here, and you simplify it. You will get this result. Okay, use this result here, okay, and express gamma in terms of p. Okay, then you substitute. So v vector v will be equal to vector p divided by m gamma, and gamma through this relation we know as a, we can write gamma as a function of p. Okay, you substitute here. Okay. So your job is to write v as a function of p. I have written v square here, not v. Okay. So you use this relation to calculate gamma. Once you know gamma, you substitute here. So you then v's are known in terms of p's. Substitute that here and show that it is a simple exercise. That's why I'm not doing it. Okay, show that this is equal to p square c square plus m square, okay, c to the power 4 half square root. Okay, clear? Okay, so this matches with our definition of energy. Okay, here, and the positive root has come because here I have considered only plus sign. Okay, when I square it, I will consider with plus sign. That's why there is only positive square root. Okay, so you complete this exercise. Okay, so your job is to just invert this relation, substitute v in terms of p. Okay, also substitute the expression for Lagrangian in terms of p and arrive at this relation. Okay, so we know now equation of motion, we know canonical momenta, we know Hamiltonian. That's it. Okay, so the dynamics is prescribed now. Okay, from the Hamiltonian you can compute, one can calculate the Hamilton's equation of motion, and Hamilton's equation of motion you can actually show that these are equal to this Euler-Lagrange equation of motion, same as Euler-Lagrange equation of motion. Okay, is it clear? Okay. So this is the equation of motion, canonical momenta, and Hamiltonian for relativistic free particle. Okay, note that we started with this relation. We started with the action, okay, in Lorentz invariant form. Then we express the action in terms of coordinate time. Okay. From that, I extracted the Lagrangian. From the Lagrangian, we calculated the equation of motion. Okay. Also, from the Lagrangian, we know canonical momenta. Okay. Then we use what is known as Legendre transformation, okay, to calculate the Hamiltonian. These are basically Legendre transformations. Okay, and we calculate the Hamiltonian. Okay, so everything is consistent with our earlier definition of three momenta, canonical momenta, and energy. Okay. Any question so far? If time permit, I will come back to this. I will come back to this exercise later. We'll see. Okay. Yes, there was a question.
The four moment of photon, how to calculate it?
Huh? Pardon? What is
The
the question?
four momentum of photon.
For momentum of photon, you basically use this relation. Okay. For momentum is see the for photon or for massless, for that matter, for any massless particle. Okay. What this relation tells you? You consider this relation: p mu equal to m square c square. Okay. This for m equal to 0 implies p mu equal to 0. Okay, this satisfies this condition. Okay, right. So from this relation you will see that E is basically this. Okay, E is basically with factor apart from factor c square. Yeah. So E is basically just let me write. Yeah. So E by C. So let me just write some steps. E by C, okay, equal to m gamma C. That is your P0. Okay, clear? So you see from this relation, you'll see that E is actually equal to C square, the three momentum. Just let me see. I have written somewhere. E is basically PC. That is what. E is basically PC. Let us let me write. M gamma C. Yeah, correct. Okay, so from this relation, okay, what you will get? P0 square minus vector P square is equal to 0. Okay, so P0 square minus vector P square equal to 0. So P0 square equal to P square. Okay, so the magnitude of P0 is basically the magnitude of vector P. Okay, but what is P0? P0 is E by C. So E equal to C times magnitude of vector P. That's it. So this is how you, for massless particle, your energy and momentum are related by this. Clear?
Sir, the Hamilton equation we have derived, is it Lorentz invariant?
Hamilton equation, see, equation is not, see, okay, let me go to Hamilton. You are asking about the Hamiltonian, right? Yeah, Hamiltonian. Hamiltonian, this is Lorentz invariant quantity, right? P square C square plus M square C to the power 4, E. Okay. See, when you go to Hamiltonian formalism, you fix T, you at equal time slices, okay, you calculate the Hamiltonian, okay. It will not be manifestly Lorentz invariant. This quantity will not be manifestly Lorentz invariant. Okay. In fact, this will come as a zeroth. This is just a energy, right? So it is zeroth component. E behaves as zeroth component of 4 vector. Okay. So this is not Lorentz invariant quantity. It will transform as a zeroth component of 4 vector. Okay, but your equations are these are Lorentz invariant equations. Okay, you cannot see that because we have at this state we have written it everything in terms of coordinate time. Okay, this is not Lorentz, this is just energy. Okay, energy transform as a zeroth component of 4 vector. Okay, similarly pi will transform as 3 component of vector p transform as usual under Lorentz transformation. This will transform as a vector. Okay, however you can see that together. Okay, you consider if I form the equation, if I take this equation and if I take this equation, okay, and if I differentiate this with respect to time, you will get the conservative dE by dt, you will get 0. These together will be Lorentz invariant, or at least Lorentz covariant. I will come to that. There is a difference between Lorentz invariant and Lorentz covariant. Okay, they will together transform as a 4 vector. As it stands, this is not Lorentz invariant quantity. Okay, remember this is not a 4 vector, this is 3 momentum square. Okay. So you have m square c square which is Lorentz invariant, but there is this p which is not Lorentz invariant. Okay. Have I answered your question?
Yes, sir.
So please keep track which quantity is Lorentz invariant and which quantity is not Lorentz invariant. Okay. P mu is Lorentz invariant quantity. Okay. How we define P mu? P mu is P0 and vector P. Obviously, this will not be Lorentz invariant quantities, right? Separately. Okay. Or for that matter, any function of P0 will not be Lorentz invariant. And any function of P is also not Lorentz invariant. At least manifestly not Lorentz invariant. One can consider some combination of them to make Lorentz invariant quantity. Clear? Good. Okay. Now we consider, okay, now consider a particle that moves in electromagnetic field. Consider a charged particle dynamics of charged particle in electromagnetic field. Okay, so I have electric field and I have magnetic field. And let us consider a particle, okay, with say charge E, not necessarily a charge of electron. Instead of Q, I'm writing E. This is the charge of a particle. Okay. And my aim is to construct action for this system. What is my system? The electromagnetic field is external electromagnetic field. Okay. That means, okay, I will explain what do we mean by external electromagnetic field later on. Okay. I have external electromagnetic field and some charged particle is moving in that field. And the velocity of charged particle is high enough that that the Newtonian description is inadequate. So we have to use rules of special relativity. Okay, so that is my system. So I have high energy, high energetic charged particle moving in given electromagnetic field. And now I want to construct action for this system. Okay, so the first part of the action, okay, first part first part of this action will be free Lagrangian. Free action or free Lagrangian. Okay, that means if there is no electromagnetic field, what would be the action of that particle, of that charged particle? Okay, so the free action is just what we know. Okay, uh, free relativistic particle. Relativistic free particle. Okay, that we already know. Okay, that I will call as L free or S free. Okay, which is given by minus mc square dt square root of 1 minus v square divided by c square. But apart from this, since there is electromagnetic field, and electromagnetic field we know that it interacts with charge, I will be having some S interaction, interacting the action for interacting part. Okay, and that I don't know yet. Okay, we have to construct this. So our aim is to find S interaction such that this is Lorentz invariant. This action should be Lorentz invariant and obviously dimensionally correct, and it should be Lorentz invariant. And if I calculate Euler-Lagrange equation of motion from this action, okay, I should get the familiar equation of motion should produce. What do you expect? What is the equation of motion for a charged particle in electromagnetic field? What law it satisfies? Or if a particle is moving in electromagnetic field, what rule it satisfies?
Lorentz force.
Maxwell law.
Lorentz force law. Okay, so equation of motion should reproduce dp by dt equal to eq vector E electric field times charge plus E by C V cross B. Okay. Here I must get this as a equation of motion. Okay, but now my action should be relativistic invariant, and if I turn off the electric field, I should get back this S free. Okay, it tells you that the charge will not come as a multiplying factor to this. Okay, because if I put the charge equal to 0, if I consider chargeless particle, this part must survive. Okay, so whatever it comes, it should be addition to this. Okay, so my total action must be additive. S interaction plus SF. Okay, there should not be any term depending upon charge here. Sorry, here. Okay, and it should be Lorentz invariant. This S interaction should be Lorentz invariant. Okay. Further, suppose if I consider a particle, suppose if I yeah, so I think I should erase this. Suppose if I consider the particle which is moving at non-relativistic speeds, that means slow moving charge particle. Okay, or for that matter, you consider a particle at rest. What do you expect? What would be the energy or potential for a particle at rest? In electromagnetic, I have a particle which is at rest. Okay. The magnetic field will not come into the picture. Okay.
Only electric potential.
Only electric potential. So you will be having V equal to minus E and phi, where phi is scalar potential. So when I take non-relativistic limit, I must get back to this. Okay, as the potential energy. My potential energy must be this when I take non-relativistic limit. Okay, but my aim is to form the Lagrangian or the action for a interaction, for the interacting part. Okay, what should be the form of L interaction? Or for that matter, S interaction. Remember, we have these following conditions. It must be Lorentz invariant. Okay, it must reproduce the correct Euler-Lagrange equation of motion, that is Lorentz force law. But that is further the final step. In between, we should take the non-relativistic limit, and we must get back to this as a potential energy. Okay. So what should I write for S interaction? Let us start from S interaction. Okay, let us start with our from the quantity we know. Okay, so I'll put here d tau. This is Lorentz invariant quantity. Okay, so if I express this in coordinate time, it will give me a factor of 1 over gamma. So it will, if I write in the coordinate time, I will get dt square root of 1 minus v square upon c square. Square root of 1 minus v square upon c square is just 1 over gamma. So I will get dt by gamma. Okay. But there is no electromagnetic field coming. So I need to write something here. Okay, and that something, since this is Lorentz invariant, that something must be Lorentz invariant in its own right. Clear? Okay, this is Lorentz invariant quantity. So I need to put something which mimics the electromagnetic interaction, which take into account electromagnetic interaction, and that part must be Lorentz invariant in its own right. Okay. Now, one way to form Lorentz invariant quantity is to take Lorentz scalar, say phi. Not this phi is not same as this phi. You consider a Lorentz scalar. Lorentz scalar. That means under Lorentz transformation, that quantity should not change at all. Or you consider two Lorentz vectors, instead of writing Lorentz vectors, I will write, you consider 4 vectors and take appropriate and build appropriate scalar from these 4 vectors, right? Or one can take tensor of rank 2. Okay, 2 tensor of rank 2. Okay, one is contravariant and one is covariant, and build a scalar. There are several possibilities. But what we have in our system, we have a particle which is moving. So I have 4 velocity u. Okay, and then I have electromagnetic field. That's it. What else we have? We have a charge E. Okay, I have 4 velocity, and I have electromagnetic field E and B. Okay. This E and B part I can also express in terms of scalar potential phi and vector potential A. Okay, So either you give me E and B or you give me phi and A. Although there is small difference, okay, between them, but let us neglect that at this moment. Okay. So I have electromagnetic field. That means I have scalar potential and I have vector potential. Okay. So these are the quantity I have. Obviously, the charge is conserved. Okay. You go from one frame to another, the charge is conserved. So the charge is really the Lorentz scalar. Okay, it's just a conservation of charge hold in relativity also. Hmm. So I have 4 vector u mu, okay, and I have vector potential phi and vector potential A and scalar potential phi, or I have electric field and magnetic field. Okay. Now I need to construct the 4 vector. I cannot construct the 4 vector out of this. 4 vector which should take into account both electric field as well as magnetic field, right? So suppose if I want to construct 4 vector out of this, I should not consider this something like this, right? This will not form 4 vector because where are the other 3 components of B? Okay, so it is futile attempt to construct a 4 vector out of E and B. One can construct something else from E and B. They are not useless quantities. One can construct something else from this. Okay, and there is also different way to construct this action through E and B. Okay, but maybe we'll discuss that later on. Okay, so I have phi and A. Let us concentrate on this. Suppose if I form, okay, a 4 vector which I will write as A mu, which is whose zeroth component is phi and its 3 component is your 3 vector potential, vector A. From phi and A, okay, I will construct a 4 vector. Okay, given by A mu, which is phi, whose zeroth component is phi, and 3 component of space component of this A mu is vector A, vector potential. So A0 is phi and vector A is your usual vector potential. Okay. And now I can construct a scalar out from u mu and A mu. Okay, so I'll construct u mu A mu. But this is not a dimensionally correct, so I need to put charge somewhere. Okay, I will put a minus sign for convenience, and I will consider this. This is for dimensionality. You will see that this will have a correct physical dimension. This entire quantity will have correct physical dimension. I must tell you at this moment that this way is a guesswork. Okay. Somebody might ask me what I can construct this. This is also Lorentz scalar. Okay, so are the higher powers in U's and A's. Okay, so this is linear in A, this is quadratic in A. This is linear in U, this is quadratic in U. Okay, as far as Lorentz invariance is concerned, I must allow these terms. These, if I allow this term, then why not this? Okay, then why not this? All these are plausible terms as far as Lorentz invariance is concerned. But then we have the experimental constraints. Okay, it must produce correct Lorentz force law. That Lorentz spelling is different than your special relativity Lorentz. Okay. This action must produce correct Lorentz force law. Okay. So with that, I will exclude terms like this. And also, these are quadratic in A. So the force equation which we will get will not be linear equation. But we know that in the equation of motion for a charged particle in electromagnetic field is a linear. Okay, namely it satisfies principle of superposition. Okay. So I will exclude terms like this. Okay. Okay. So from the scalar potential phi and vector potential A, I construct A mu. Okay, and I take a Lorentz scalar built from A mu and 4 velocity U mu. That is same as writing U mu and A lower mu. Okay, now this quantity is Lorentz invariant, so is, and this quantity is manifestly Lorentz invariant. Okay, so this is my S interaction. But there is one term which is possible, okay, which is not higher order, okay, and still it is Lorentz scalar. Okay, suppose if I consider A mu x mu, there is a coordinates also, right? There are coordinates apart from 4 velocity. I have 4 coordinates, right? So I can construct this quantity also. But you see that if I put it here, the action is not translationally invariant. So your free part is translationally invariant. So this is not translationally invariant. It depends coordinate explicitly, coordinate of the charged particle explicitly. So it is not translationally invariant. So I exclude this part. Okay. So this is my action. Okay. So my Lagrangian L interaction will be okay. So let me write L interaction in next step, but first let me write this Lagrangian in a nice form. So S interaction is equal to minus, I can also write this as minus E by C. Someone is what is the time? 13:40 is 1:40. So 12:30 to 2. That is our time. So this meeting is from 12:30 to 2. So I still have time. Okay. So I can write this in this form also. I can write this as A mu dx. Okay. Okay. You can so one can write this combination dt by gamma u mu, okay, as dx mu. Okay, it's easy to show this thing. Okay, so this is another form which is same as this, just written in slightly different way. This is equivalent to this. Okay. Okay. Now I will write this in LDT form. We will write this in LDT form. Okay. But before writing in LDT form, let me write the full action. The full action will be S equal to S free plus S interaction. What is S free? S free is integration, so minus mc square integration dt 1 minus square root of v square divided by c square, okay, plus s interaction. S interaction is minus e by c, and let me write now let me use this and expand it in component wise. Okay, if I expand it in component wise, what I will get? I will expand it in component wise. Okay. So this is equal to correct. Let me expand which quantity? This quantity. Okay. Expand this in component wise. Okay. So this will be equal to u0 a0, okay, minus, okay, u dot vector a. Okay. Yeah. So this is just the expansion of this, and then there is this gamma factor. 1 over gamma is coming, so I will write it 1 over gamma. E by c 1 over gamma dt is there. Okay. So this part complete. Okay. I have just expanded this term in components. And let us substitute the expression for u0 and convert this into 3 velocities. Remember what is u? U is 3 component of 4 velocity. This is related to your usual 3 velocity by this factor, gamma v. This is dx d vector x by dt. Okay. This is 3 component, spatial component of 4 velocity. So take this thing into account and remember what is u0. u0 is same as u lower 0, that is dx0 by dt. Okay, dx0 is c dt divided by dt, so you just c. Okay, so there's some, I think there is some problem. u0 is gamma, yeah, just a minute. u0 is problem, just a minute. Okay. U mu is equal to dx mu by d tau. Okay, so u0 is dx0 by d tau, that is c dt by d tau. Dt by d tau is gamma. So c gamma is u0 and vector u is d vector x by d tau, but that you can write as gamma dx by dt, that is v. Okay. Clear? Now substitute this and this here. Okay, so you'll get minus mc square. So I should write this, really is the wrong way of writing somehow. It is, I should write it minus mc square to first term, attached to first term. So let me erase it completely. Okay, so let me write s again. So first term is free part, minus mc square dt square root 1 minus v square divided by c square. Then there is s interaction, that is minus e by c integration dt 1 over gamma, okay, and u0 a0 minus u dot a. Now you substitute for u0 and vector u, and noting that a0 is just phi scalar potential, we get mc square dt square root of 1 minus v square divided by c square, okay, minus e by c dt, okay, 1 over gamma, okay. Then I will get gamma c phi scalar potential minus gamma vector v dot a. Okay, so this is minus mc square dt square root 1 minus v square divided by c square minus c will go, so it will be, so this I will write as plus dt e by c, okay, into a dot v, okay, minus e phi. So this will be the final expression for action. Is this clear? Okay, so I have written the full action. Full action contains the action for free relativistic particle plus the interaction of that relativistic particle with electromagnetic field. Note that in this action there is no part which tells me the dynamics of electromagnetic field. Okay, this part tells you the dynamics of particle. Okay, this part, this both terms. If I calculate Euler-Lagrange equation of motion, what Euler-Lagrange equation of motion I will get? I will get Euler-Lagrange equation of motion for that particle. Correct? Okay. There is no term or no part which will give me Maxwell equation, which really represents the dynamics of electromagnetic field. Okay. In this sense, our electromagnetic field is external electromagnetic field. There is no dynamics involved. Okay. It is given to you once and for all. Okay. Clear? On the other hand, you have the dynamics for the particle. Okay. So I hope the term external electromagnetic field is clear. Okay. So now from this you can just extract the Lagrangian. So the L is L free, okay, that is minus mc square 1 minus v square divided by c square, okay, plus e by c a dot v minus e phi. So this is the Lagrangian for electromagnetic for a relativistic particle in electromagnetic field. Note that this is not in manifestly Lorentz invariant form, or Lorentz even it's not written in 4 vector notation, but everything is hidden here. If you construct the action, then that action is Lorentz invariant. Only thing is that I have not written in that form, in manifestly Lorentz invariant form. If you want to write in the manifestly Lorentz invariant form, then you can use this. Your starting point will be this. Use this as a S interaction and use this part as action for relativistic free particle. So free part will be this, and the interacting part will be given by this. That will give me the manifestly Lorentz invariant Lagrangian or action. But we have written in coordinate time, so we don't. But still my action is Lorentz invariant. That is the important point. Although I have written in this form, okay, my action is still Lorentz invariant. Okay, is it clear? Okay. Now, once I have the Lagrangian, or once I have the action, we start our usual analysis. Okay, you determine Euler-Lagrange equation of motion. Okay, what we need? We need del L by del xi dot. Okay, then we need del L by del xi. Okay, and then we need ddt of del L by del xi dot. That's it. If we know this, then one can easily obtain the equation of motion, the canonical momenta, and the Hamiltonian. Okay. One should be careful now. This phi is a function of t, x1, x2, x3. Okay, so it is a scalar function of space-time coordinates. And similarly, vector potential is also a vector function of space-time coordinates. Okay, clear? So suppose if I face with this term dA by dt, it will be del A by del t plus del dx I by dt and del A by del xi. Okay, one should be careful here. X3 coordinate is a function of time, A is a function of t and x. Okay, so total derivative of A is partial derivative of A with respect to time plus this. Okay, and similarly for phi. So one should keep in mind this. Okay. With this, let us calculate del L by del xi dot. Okay. So what will be the del x by del xi by del L by del xi dot? This action of del xi dot on this part we already know. Okay, that gives me m gamma vi. Okay, that we have seen free part m gamma vi. Okay, I want the extra piece which is coming from the action of del xi dot on this. Okay, so let us see what we get. Okay, a dot v is ai xi dot. Okay, so del xi dot of a dot v is ai, right? So it is del xi dot. I'm really going slowly, okay, because this is a first time calculation for you. Okay, so this del xi dot aj xj dot. Okay, so I will get Kronecker delta ji. So I will get ai here. Differentiation of this with this, and since we have only ij case, it doesn't matter whether we use up or down. Okay, here for vector a mu is, our convention is a upper mu is phi and vector a, so it implies that a lower mu is phi and minus a. Okay, but if I have ai, okay, in calculation everywhere, if I have three components, then it doesn't matter whether I use ai or ai really. Okay, clear? So differentiation of A dot V with del del xi dot I am get is AI. Okay, and differentiation of del del xi with del del xi dot with phi is 0. Okay, there is no term, no contribution coming from this term. So I will have just E by C AI. Okay. Now d dt of this d dt of del L by del xi dot. That means I am calculating now this term. Okay, is what? D dt of this term is really dpi by dt, where pi is m gamma vi. We have done that already. Plus E by C dAI by dt. Okay, is that clear? Is it clear to all this calculation?
Yes, sir.
Okay. now I have to substitute. Now I have to use this property. Okay, so this is equal to dpi by dt. By the way, when is your next class?
3
3
p.m.
p.m.
3. So you just okay. So I will take for 5 minutes and then I will stop. Okay. So dpi by dt plus E by C. Okay, d dt of AI. So it will give me del AI by del t. Okay, plus dxi by dt. Okay, into del AI dxj by dt and del AI by del xj. Okay, so I will get, but dxj by dt will be jth component of 3 velocity vj. And then I have del AI by del xj. Okay, clear? Now let us concentrate on this piece. Further simplification is required for this term. Okay, that we will do. And del L by del xi will be equal to no contribution will come from here. Some contribution will come from here and some from here. Okay, because this A will depend on this vector x. Hence, there will be some contribution to this term. Okay, so it will be E by C del del xi of A dot V. Okay, minus E del phi phi del xi. Okay, now so this equation and this equation we need to simplify it. Okay, we will simply in the next class we will simplify these two equations. Okay, and we will arrive at the Euler-Lagrange equation of motion. In between, I will just tell you, I will anticipate, okay, and tell you that we need to use this definition, and I hope you are familiar with this. Electric field is minus grad phi, okay, minus E by C del A by del T. I hope you are aware of this definition of the electric field, and the magnetic field is curl of A. Okay, these two things we need to use. Okay? We will use that. Okay, another thing which I should tell you is that I also need the expressions for suppose if I have two vectors A and B. Okay, if I want to take cross product A cross B, okay, there's a simpler way to do this. Okay, You just consider epsilon I j k a I b j, where epsilon I j k is Levi-Civita, three-dimensional Levi-Civita symbol. Okay, it is 1, 2, 3 equal to 1, and any even permutation of 1 to 3 equal to 1, and any odd permutation of 1 to 3 is minus 1 or even, and it is totally antisymmetric. Okay, so with this property of epsilon ijk, okay, one can express cross product like this. So this will be the kth component of A cross B. It is written as epsilon ijk ai bj. You can easily check that. Okay, kth component of cross product kth component of A cross B is epsilon ijk ai bj. Similarly, curl of some vector A will be epsilon ijk, okay, del I, okay, del j. Suppose if I want ith component of this curl, okay, then it will be epsilon ijk del j ak. Okay, clear? Then we may face with terms like this: A cross B cross C. Okay, this also one can express in terms of epsilon. Okay, so suppose if I want ith component of this, okay, ith component of this will be what? We know kth component of A cross B. Okay, so keep this as one vector and keep this as another vector, B cross C. So it will be ith component of this entire thing. So it will be epsilon I j k, okay, A I and B cross C k, kth component of B cross C. But this is equal to epsilon I j k A I B cross C, kth component of B cross C. Kth component of B cross C is another epsilon. Okay, and you use this time different indices. Kth component of B cross C therefore will be equal to BL, kth component of B cross C will be epsilon K L M B L C M. So we should know how to combine two epsilon ijk, epsilon KLM, and note that there is a sum over K involved. AI BL CM. Okay. Okay. Now epsilon ijk, epsilon KLM, one can show. Okay, I will give this as an exercise. Okay, one can show that epsilon ijk, epsilon KLM equal to, see, as far as this is concerned, Isaac is concerned, it is antisymmetric in interchange of any indices I, J, K. This is also antisymmetric under the exchange of any two indices K, L, M. Okay, fine. So I need to write some expression which take care of this antisymmetry. That's it. Okay, so I will write, show that this is equal to delta I, there is a sum over K involved. So I will write this as delta IL delta JM Kronecker delta minus delta IM and delta JL. Okay, this will be the expression for epsilon ijk, epsilon KLM sum over K. You can see now that right hand side have appropriate symmetry property. Okay, if I interchange I and J, Okay, if I interchange I and j, what I am going to get? Delta j. In the first term I will get delta jl delta im. Okay, and in the second term I will get delta jm and delta il. Okay, but this is just minus of delta I delta jm minus delta im delta jl. Okay, so hence under the exchange of ij, okay, it is antisymmetric. Okay, here under the exchange of lm, see the k is summed over, so you don't have to bother about k is summed over. Okay, we will be, you write it in components, it will be ij1 epsilon 1 lm plus epsilon I j2 epsilon 2 lm and so on. Okay, so you don't have to exchange k with anything. Okay, you just interchange free indices. So these are the free indices. Okay, so if you interchange ij, you should get minus sign. Indeed, we are getting minus sign. If you interchange ln, one can show that you will get a minus sign. So right hand side have the properties of epsilon, this Levi-Civita symbol. On top of that, if I write component wise, that means you consider epsilon, put I equal to 1, j equal to 2, okay, and k, and say L equal to 2 and m equal to 3, and say k. Okay, from these we should know the value of this. Okay, that same value we will get if I use this expression. For example, epsilon 1 to k, epsilon k to 3, you will be equal to epsilon 1 to, what value k can take here? Okay, 1 2 is already used. If I use 1 here, then I will get 0. If I use 2 here, then I will get 0, because 2 2, no indices should repeat. Okay, so as far as first term is concerned, k must be 3, but as far as second term is concerned, k must be 1. Okay, so no matter what value of k we take, I will get 0. Okay, so epsilon 1 to k, epsilon k to 3 must be 0. You check that, you will get 0 here. Indeed, we are getting 0. Okay, so delta 1, L is, I is 1 and L is 2. Okay, L is 2. I is 1, L is 2, and J is 2. Okay, and M is 3. Okay, J is 2 and M is 3. Okay, that is first term, minus I is 1, J is 3, M is 3, and J is 2 and L is 2. Okay, so this combination, delta 1 2 is 0, delta 2 3 is 0, delta 1 3 is 0, so you will get 0. Okay, and hence for all the values of I and j, so you take all the values of ij. All the values of ij means if I equal to 1, then j must be equal to 2. If I equal to 2, then j must be equal to 1. If I equal to 3, then j must be equal to, yeah, j must, here j can be 2 or 3. Okay, if I equal to 2, then j can be 1 or 3, and so on. Okay, you take all these values of I and j, you take all the values of L and M, and so that you reproduce the same result with this expression. That I will leave it as an exercise. Okay, so we need to show correct Lorentz force law from this as Euler-Lagrange equation of motion. We need computation like this. Will the calculation will involve term like this. Okay. Okay, so I will stop here, and you go through this calculation and finish this exercise. I will stop here and I will let you know the timing of next class. So tomorrow 2 o'clock you have MMP, okay, and morning what classes you have?
Sir, there is mock test tomorrow.
Uh-huh.
Mock test tomorrow. In that
Mock test.
at
So when is it?
10:30.
Okay, so fine, 10:30. So tomorrow morning we will not take. So tomorrow evening also you are booked and 2 o'clock also booked. So tomorrow I am not going to take any class. Okay. So day after tomorrow this MMP2 that half calculation is remaining, that I have to finish it. Okay. That I will see. Maybe day after tomorrow I will take a class. And AQM we will see how when to take. Maybe day after tomorrow again I will. Yes.
So is it possible for you to send some last year question papers so that we know what kind of questions to expect in internal question papers for
MMP2?
AQM? No, AQM, sir.
AQM, no, AQM I have not taken, right, last year. AQM last year Professor Durganandani took.
So can we ask her?
No, but the way she takes and the way I'm taking will
Yeah,
be
exactly.
different. So there is no point in taking the question paper from last year. So we will give whatever I discussed in this class, I will give the question which depends on this discussion. Okay.
Okay, sir. And so for problems on tensor, what book to refer?
Tensor, I told you that I am not going to ask, as far as this course is concerned, AQM, I am not going to ask deep questions from tensor. The calculation will involve contraction, okay, check whether the given quantity is a tensor or not, and so on. So for that, I think Jackson, the problems are not given. You can use, there is a simpler book just for this coordinate tensor. You can use Bose or something, mathematical physics, Bose. Okay.
Okay, sir.
Bose or BOAS. Okay. Bose.
Mariel Bose.
That is one book, and Arfken is there. Arfken is another.
Okay, sir.
Okay. So you use these, okay, just for a computation. Okay. But they may not have discussed the tensors in special relativity. Overall tensor they must have discussed in great detail. Madam is also doing, but tensors in special relativity they have not discussed, I think. Okay, but once you understand the concept of tensor, it's not difficult to implement it in special relativity, right? Okay.
Okay, sir. Thank you.
So, any other question? Please try to solve or try to read Jackson and Landau and Lefschetz. Okay. This current part I am taking from Jackson and Landau and Lefschetz. Okay. Landau and Lefschetz, Classical Theory of Field, Volume 2. There are 8 volume or 9 volume book or series of Landau and Lefschetz. Okay. So Volume 2. Please read that. Please read the relevant part. Okay. Any other question? Please tell me, please give me the feedback. I don't know how is it going, whether it is going too fast or with appropriate pace, slow pace, I don't know. So please ask the question, give me feedback. If you have some problem, tell me now. Okay, I will adjust accordingly. If you are not understanding something, if from my side if there is some lag or some problem, then please feel free to tell. Okay.
Yes, sir.
Okay, so I will end the meeting.
Sir.
Yes.
Sir, you were going to explain about